Thanks. So, hi everyone, welcome to the Statistical Society of Australia's first member-only webinar. I'm Susanna Cram, I'll be the chair for today. Thank you for joining us. So it's a privilege to have Andrew speaking today, and we will be doing questions slightly differently. You're still very welcome to type your questions into the chat window and I'll read them out to Andrew, or you can raise your hand. And the way you do that is you click on the participants down in the bottom middle of your screen, and then there's an option within the box that pops up, a little button you can click on that says raise my hand. So we're likely to actually have 2 question times this time. So about halfway through, we're likely to have an option to raise any questions at that stage, but then also at the end, there'll be time for questions as well. So Andrew Zammit-Mangion is an ARC DECRA Fellow, Senior Research Fellow, with the School of Mathematics and Applied Statistics at the University of Wollongong. He has vast experience in spatio-temporal modelling, and including releasing a book on this very topic last year, which I would encourage you to check out. So over to you, Andrew, and thank you so much.
All right, yeah, thanks, Susanna. Thank you for the invite. It's the first time I'm giving a webinar, so I'm very curious to see how it goes. What I'll be talking about today is joint work with Christopher Wikle, the University of Missouri. Chris Wikle has much more experience than me in spatio-temporal modeling, and is also interested in the interface of spatio-temporal models. So we kind of have a joint interest. We came to it independently, but we thought that it would be good to have this joint work together. The title of this talk is Probabilistic Spatio-Temporal Forecasting Using Deep Learning Models. So there's a lot of words in that title, and all of them mean something. So the first word, probabilistic, is because we are interested in uncertainty quantification. So we don't just want a model that predicts, but also which gives us some quantification of how uncertain we are in our forecasts. Spatio-temporal because we are interested in spatio-temporal applications. Forecasting because we are interested in forecasting the future. And deep learning models because we are interested in this interface between statistical models and these machine learning models that are often used to great success in the computer science and AI communities. All right, so let's see. So go start off with a brief introduction on space-time data. So many environmental and social phenomena evolve in both space and time. So you can think of environmental variables like temperature or rainfall. These things happen at a certain location in space and at a certain time point, and we can many times use the information on how they are spread in space and time to actually forecast what's going to happen in the future, and also predict what's happening at places that we don't observe. And this is prediction in space and time is the primary goal of this field of spatio-temporal statistics. So in essence, what we want to do is use the dependence in space and time to better forecast what is going to happen in the near or long-term future. And we do this usually by using models. And these models can sometimes encode scientific understanding and prior knowledge that we have about the physics of the system, for example. So I like to show this this picture because it really gives an idea on how the diverse range of applications that spatio-temporal statistics can play a role in. Of course, in the middle, we've got this big picture of Earth, and you can see the clouds which are swirling around, and there's lots of dynamics there. There's wind, there's pressure, and it's basically controlling weather, and on much longer time scales also our climate. So that's the kind of the obvious domain where spatio-temporal statistics fit, but we can also think of things like epidemiology, crime, conflict. I've worked a lot on sea level rise, so I looked at, for example, how and where Antarctica is melting and how that is contributing to sea level rise. And it can also try to answer really important questions like how severe is the drought we are currently in, and how long is it likely to last, and so on and so forth. This is just an aside. Many times we focus on modeling spatio-temporal systems in isolation. So for example, we try to model sea surface temperature, or we try to model ocean color, which in this case is a proxy for phytoplankton density. But everything is interconnected in the world, and there are actually ways in which to model jointly these processes which are interacting. I won't be talking about that today, but it's good to keep in mind that things don't happen on their own. There's always some interaction going on, and if we could model things jointly, then probably we could get even better predictions and better forecasts. All right. So there are several modeling strategies. As I said, the model is the main component that we're going to use. The traditional space-time model is a partial differential equation. And if we think of a linear partial differential equation, such as the diffusion advection equation, then this is kind of the most natural way of thinking of a process, which is diffusing in time or moving in time. The diffusing, you can think of having some butter in a plate, and it warms up and it kind of melts. That's the diffusion action. And then you can actually tip the plate and the butter starts flowing down, then that's the advection part. Okay, so diffusion and advection can really be used to explain a lot of what we see around us. Of course, these diffusion and advections, they change in space and in time. So this is the really big problem. So these partial differential equations have got many parameters, such as diffusion coefficients or advection coefficients, and they're not constants. They are fields in themselves. So they are changing themselves in space and in time. So estimating these concurrently with the process which you are trying to predict is very, very challenging. And solving the PDEs in themselves can be difficult and time consuming as well. So here I'm going to just show you briefly what a typical space-time system, let me see how I do this. There. Okay. So what I've got here is a picture of sea surface temperature in the North Atlantic Ocean. And what I'm going to show you is an animation of how the sea surface temperature evolves in time. And what you should look out for are these kind of advections, like the motion of temperature, if that makes sense, and also the diffusion of the temperature, how it is spreading. And the directions and the rates at which things diffuse are changing in space and in time. So it's really complicated patterns, and this is why space-time phenomena are quite hard to model. What we are seeing here is what's known as a data assimilated product, where satellite data of sea surface temperature has been assimilated or combined with the solution of partial differential equations to kind of give you the optimal solution. So this product is probably a very realistic version of what is going on in sea surface temperature. And we'll be using this data later on to test our models, predict and forecast what sea surface temperature is going to do in the future. Okay. All right, so we want to forecast a system. We want a forecasting system. And I said that these parameters are really annoying. They are there, but of course we need them. We need to know what they are to accurately forecast what's going to happen in the future. So ideally we have a system that does not require parameter estimation. Yeah, we were talking about this forecasting system that ideally precludes the need for parameter estimation and is computationally efficient. And such a forecasting system does exist. Ideally, it expresses these parameters, so the diffusions and the advection coefficients, as functions of the previous process behavior. So the idea is, if you see something moving from left to right, let's say water moving from left to right, then you know that the advection parameter is one which yields a process behavior that moves from left to right. And if you see things which are like the butter, if it's melting quickly, it means it's very hot. If it's not melting quickly, it means it's not hot, right? So is there a way that we can actually look at what's happening and directly get the parameters from that behavior? And of course, this mapping is an extremely complex mapping or extremely complex function, right? And you know, me or you wouldn't be able to come up with this, but this is where deep learning models come in. So deep learning models are just models that can encapsulate really complex representations. And so what we are going to try to do is actually make a deep learning model, and actually somebody else did this, and I'm kind of going to add something to that later, which looks at the previous process behavior and automatically gives you diffusion coefficients and advection coefficients, okay, automatically. Right. So there is some maths involved, and I'll try to give you the intuition behind it rather than focus on the details. But this first equation is very, very important. So this is the advection diffusion equation. And it basically tells us, the solution to this PDE tells us how a process Y in time t and space S is evolving in space and time. And the two key parameters of interest are D here, which is our diffusion coefficient, and V here, which is a vector, and this vector, think of it as a wind vector, tells us how fast the process is moving in a certain direction, and also the velocity at which it is moving, the actual speed that it is moving in a certain direction. And the solution to this partial differential equation is given by this integral equation. And you say, okay, so y at time t is simply the integral of a function times an initial condition y naught. And this function here, m naught, is a Gaussian kernel. That's all it is, right? So most of us in the audience would know what a Gaussian kernel looks like. You've got this variance parameter, so the diffusion, you can think of it as how wide this kernel is. So the bigger the diffusion coefficient, the more averaging it's doing over space, so the more diffusion you get. And V is displacing the mean of the kernel, and if it is displaced off the center, then things are going to move. So it's got a very nice feel to it, this Gaussian kernel, and it appears in this integral solution over here. So this is in continuous time. T can take any value, but we can discretize. We can think of a discrete system by simply taking t to be the integer. And if we do that, we're simply going to set the initial condition to yt, and then say what's going to happen at yt plus 1. Then this interval is simply 1. So I'm going to just substitute t equals 1 in this equation over here. And what I get is this kernel. Okay? So this is a discrete time spatio-temporal process, perfectly valid. And it can represent diffusion and velocities, okay, which are constant in space and constant in time. So it's a very simple model, but nonetheless a model. And it's also a deterministic one. So if I give you yt, I can tell you exactly what yt plus 1 is. All right. So what do these things look like? So this kernel, go back here. So this kernel over here really determines this behavior of the space-time system. So I already explained what D and V do, and we can see what happens in a one-dimensional space setting. So what I've got here are 4 scenarios, 4 different kernels, and I'm just simulating some random field. At every time point, I'm adding some more random disturbance just to give it a bit of a kick here and there. But this is what the different kernels do. So a very narrow kernel means you've got a very low diffusion coefficient. It's centered at 0.5, which means there's no advection. So what you get is sustaining of the field. So what I'm plotting here is time on the y-axis and space on the x-axis. So as time is going on, you know, things are not disappearing because there's no diffusion going on. Things are being sustained. Actually, if you make this kernel high enough, this thing will explode. You can have instability as well. But I've made it on purpose such that this is a stable system. Now, if we are going to widen the kernel, now things are going to diffuse quickly. Okay, so imagine you get a signal and boom, it goes dead. Here you've got some signal and then it went dead. And things are not being sustained that much. If we shift the kernel to the right, we've got motion to the left. and if we shift the kernel to the left, we get motion to the right. And this is why you see these stripes over here. What that means is that there's a pulse of red here, and it's going to be shifted to the right as we go in time. So that is the basic action of this model. If you see our book and many other works, this has got a special name. It's called an integral difference equation, and we call it an IDE for short, an IDE model. So this is the deterministic version, and we're going to make a statistical version of it pretty soon. Okay, so as I was explaining, this kernel is everything, but these parameters over here, the d and the v, which I'm collecting into this vector theta, they are fixed in space and time. So this is not very realistic. If you remember the sea surface temperature, these velocities were changing all over the place. So actually these coefficients should be functions of space and time themselves. And now inference is going to be very difficult in these models. You will need highly sophisticated inference machinery such as sequential Monte Carlo. And something you can do, which tends to work very well, is actually consider only a small time window and assume that these coefficients are not changing within that time window. That also tends to work very well in practice, as I'll show you later. But the spatially varying part is particularly important. So these things tend to vary in space. Right. So I'm going to move on to what the machine learning community did to solve this problem, which I built on after that. So this paper came out in 2018. I forgot which machine learning conference it was, but the paper is freely available online. It's by Deb et al. What these guys did, they built what's called a convolution neural network. So remember, there's this very complex mapping between what the process does and what the parameters are. And the idea is to find that complex mapping. And they use convolution neural networks to do this. I'll explain why convolution neural networks are a good idea in this scenario later. But just think of it as a very complex function for now. So what they do is they take the last 3 time points and they stack them. So now you can think of your data as 3 images stacked together. If they are 64 by 64 images, then you have 3 of them. So you have 64 times 64 times 3 data points. That's right. And then you're going to pass it through this black box. And what it's going to spout out is actually a map of the diffusion coefficients and of the velocity coefficients. Assuming that you know what this map is. So you've already trained your convolution network to find that mapping. Well, once you know what these diffusion coefficients and advection parameters are, well, then you can put them into the integral equation to give you what's going to happen to the next time point. And then you can do a recursion. So you take this next time point, put it in as the last image, pass it through the convolution neural network again. It gives you new parameters, update, and you get yt plus 2. And you keep on doing that. So if this actually works, then the implications are enormous, because this means you don't need to do any parameter estimation. This convolution network is estimating the parameters for you if you want. But since it's a deterministic mapping, it actually is extremely quick. So it could give you these spatially varying parameters in a split second on a good GPU. So at first I looked at it and I said, like, I really couldn't believe it, because people like me and Chris Wikle and many others agonize a lot on how to get these representations of spatio-temporal systems that are realistic and really complex, but yet we can compute with them at the same time. But there actually is a history of CNNs, convolution neural networks, being used in this way. In machine learning, there's something known as the optical flow problem. It is the problem of tracking objects in videos. So the idea is, if you're tracking a ball, let's say in a football game, and you want to predict where it's going in the next time step, you can actually put in the last 3 frames of this football game, and it will tell you roughly in the next time frame where the ball will be. It's got implications for betting and things like that. So this optical flow problem was solved using convolution neural networks. But I believe that the De Bezenac paper was the first one which applied it to environmental problems. The reason why CNNs can work so well is because they can encode dynamical features, which in turn might have straightforward relationships with the partial differential equation parameters. At least this is my interpretation. So I'll try to give a bit of an insight into what's happening in a convolution neural network, which hopefully justifies this claim. So I've got 4 images here. At first, they might look really complicated, but hopefully you'll find that they're not. So let's say I've got this a true signal. Let's say this is a black waveform over here. This is a true signal. Okay, it's quite complex. It's got some high frequency stuff going on here. It's got low frequency stuff here, and I want to characterize it in some way. You can think I can have 2 convolution filters. One of them could be this red dashed line over here, and the other one could be this blue dotted line over here. What happens if you apply the convolution operation of this red kernel with this black signal is you get something like this. So you can see that it has totally filtered out the high frequency part. It's nearly flat over here, and has reproduced, you get a large signal where in fact you've got that big bump in the signal. So here it's got a big bump, so you have a big bump over here. On the other hand, when you take the convolution of the black signal with the blue convolution kernel, then what you get is something which recovers the high frequency part and then completely smooths out the low frequency part. And then what you can do, and all CNNs implement this, is a process called rectification, where you literally throw away everything in the bottom half axis, and then you smooth out a bit. Okay, they call it pooling. And what you end up with is the blue here is literally showing you where you had these high frequencies. Okay, so you have a high signal there. And this red kernel, so the finally convolved rectified pooled signal is showing you where you had this positive low frequency bump. Okay, so it's kind of localized in your image. Think of this as an image where a certain feature is occurring. Now, of course, we've got space and time, so we've got 3 dimensions, and therefore you need to think of a 3-dimensional kernel. Now, I don't really know how to plot that 3-dimensional kernel, so I'll try to do my best here. I've used transparency to denote the past, so something which is more transparent is further into the past, and something which is dark is in the present. So this is at t-2, this is at t-1, and this is at t. So the idea is that if you convolve this 3-dimensional kernel with a set of 3 images stacked on each other, this is going to return a large bump, let's say, in your next image, in places where things are flowing from the southwest to the northeast. Okay. So it's that if somehow in those 3 images it detects something moving from bottom left to upper right, you're going to get a big bump in that image. And that big bump tells you that your wind vector, or whatever your advection vector, should probably be like 1, 1. So for example, pointing in the northeast direction. Okay. So what you need to do is have tons of these filters. Talking about 64 filters just in the first layer, for example, which extract these features, which then hopefully have a very simple relationship to your advection parameters. So that's what you do. You put in these kernels, which you don't know what they are. This is where all the parameters come in that you need to estimate in a CNN. Okay, you need to estimate them using tons of data. And you do this, and then you pass the output of a convolution layer to another one, and to another one, to another one, to another one, until finally you relate them to the advection parameters or to the diffusion parameters. And that's done through a simple linear model. Okay, so it turns out that these convolution neural networks are indeed very capable of encoding these PDE parameters. But what De Bezenac focused on was on these noiseless, complete images. And I was very interested in the sort of space-time data we're interested in. It's noisy, there's a lot of data which is missing, and I really wanted to see whether I could put the CNN into a more statistical framework which allows me to cater for these missingness and noise in the images. So I can stop. I can stop for questions if there are any questions. Not sure.
Does anyone have any questions they'd like to ask Andrew at this stage? You're welcome to either chat in the chat window and type them in, or you can raise your hand and I'll invite you to ask your question directly. We'll give you 30 seconds. I'll keep going. Looks like your explanation's been very clear, Andrew.
Oh, I got to hear that. But you know, it's clear to me. But I've been working on this for quite some time, so I'm sure there are lots of questions. But we can wait till the end if there aren't any now. All right. So what we can do is think of the CN of. What I'm going to do, this is the starting point, is to express this integral difference equation first as a statistical one. So the first thing I'm going to do is add this component. Add this component eta t, and this is saying that even if we do have the exact model, there is some residual variation because we never have the exact model, so there's always going to be some residual variation to cater for what our model cannot explain. And that's a space-time process in itself. It doesn't necessarily need to be a complicated one, but there needs to be something when you are uncertain, when you don't have the full complete image about what's happening. Right? So that's what this is doing over here. The second thing is exactly the same as what we had before, but I've replaced m with k because it's a slightly different object. The parameters, I'm going to say that they are functions of the previous tau. These are 3. I've been using 3 images. The previous 3 time instances. So I'm postulating through the convolution neural network that if you give it the processes at the 3 previous time instance, it can give you the diffusion and the advection parameters. So these psi are actually the CNN parameters that you need to estimate. There are about 200,000 of them. Okay, in the model I was working with, there are lots of those, so you need tons of data to estimate these parameters. But this is the basic model. The important thing is that theta itself is time invariant, which means once I learn this mapping, theoretically, I could use it anywhere and everywhere in space and time. And it should work. So this looks complicated, but all I've done is I've taken the Gaussian density or the Gaussian function and replaced the diffusion coefficient with something with the output of a CNN, which is a function of the previous time instances and its parameters. The same with the velocity, and this is the diffusion coefficient again. And h here is simply this thing that we had before. This is the velocity parameter. So these would be the two outputs of the CNN, which give me the northern strength and the horizontal strength of the advection parameters. Right. So, of course, there is a limit to how much you can push this. You need to assume that these diffusion and advection parameters vary quite smoothly in space and time. If you don't do that, there's a very strong chance that you're going to overfit. Okay. So in the Debezinak, h here is simply this thing that we had before. This is the velocity parameter. So these would be the two outputs of the CNN, which give me the northern strength and the horizontal strength of the advection parameters. Right. So, of course, there is a limit to how much you can push this. You need to assume that these diffusion and advection parameters vary quite smoothly in space and time. If you don't do that, there's a very strong chance that you're going to overfit. Okay? So in the de Bézanac So what the de Bézanac people did was they added a penalty term to their cost function, which they used to optimize the CNN, which penalized for roughness of the parameters in space. What I'm doing here is slightly different, but has the same effect. If I'm going to decompose the diffusion parameters and the advection parameters as sum of basis functions, and these basis functions are smooth in space. Okay. And then what I'm going to have to estimate are these weights. This also makes the problem much easier. So if before I had 64 by 64 pixels for the diffusion, now I may have only maybe 12 basis functions or 16 basis functions. So I've reduced the dimensionality quite a lot. And then we can discretize, and from these functions we get vectors and matrices. We don't need to go into the detail. We have to discretize though, because these things can only be done on graphical processing units, and actually you need to discretize so that your images are a function, are a power of 2, so that you make maximum use of the GPUs. So in fact, I use a 64 by 64 grid. Okay. This is the sort of architecture that I used. So I give the CNN 3 images, which are stacked together. I apply it 64 convolution kernels. So I get 64 images, and each of these images now in this stack will tell me where a certain feature is strong or weak in this image. Right? And then what you do is keep on drilling down. So these are 64 32 by 32 images. I'm going to apply another convolution layer to get 128 16 by 16 images, apply another convolution layer again to get a 256 8 by 8 images. And then what I'm going to do is stack them into one long vector of size 256 times 8, so about 1,800 elements, and then fit a simple linear model to map these to the W. Okay. And then what you do is you put it in a likelihood framework. I've got a paper on this for the details. I'll show you the link later. Put it in a likelihood framework. You can apply stochastic gradient descent. If you have enough image sequences, and in my case, I had about 80,000, it was enough, you can actually find all the parameters which are appearing in the CNN quite well. Okay, and it only takes a couple of hours on a GPU. All right, so now assume, this is where statistics comes in, hierarchical modeling, that we have an irregularly spaced point set of measurements, so ZT, at each time point, and these measurements change, their location changes in time. And we have this measurement equation model or observation model. So ZT is picking out some of those YTs. So maybe you're observing the 50th pixel and the 100th pixel. That's what this H matrix is doing. And then it's adding noise to it. Okay. So this is what we observe, but we actually want to make an estimate Y and actually forecast Y at future time points. Okay. So the main task. So the IDE that we had is this, and after we discretize it, we get this. Now, for those in the audience who come from a statistics background, will immediately realize that this is a tau order Markov model. Why? Because we're saying that YT plus 1 is a function of YT at the previous tau instances. Okay? So that's a tau order Markov model, because it's stochastic, because you've got this term over here. And through a bit of matrix algebra rearranging, you can actually express a tau order Markov model as a first order Markov model, where you augment this vector to be of size 3 times the size, essentially. You get new matrices. The details are not important. The important thing is you actually have an equation of this form, where the transition matrix, which is K here, is a function of YT. And with that, you can predict YT plus 1. Interestingly, it's also a member of the general quadratic nonlinear family of models because you have a function of yt times yt. Quadratic because if this was simply yt, you would have had yt squared. But it's general because it's a function of yt. And these were investigated in 2010 by Chris and Evan, and they found that they can reproduce some very interesting dynamics. What you have to keep in mind here is that this is actually the output of a convolution neural network. That's the only difference. Right. Right, so we've got this first order Markov model, and we've got this measurement equation model. So put these two together and you get what is known as a state space model. And state space, making inference in state space models has got a long history back to the 40s, 50s, the 20th century. And this is a very special type of state space model. It's not a linear Gaussian state space model. It's not linear because you've got this complicated matrix over here. So how do you do inference in state space models which are not linear? Well, it's not easy. One of the simplest methods, though, is to use an ensemble Kalman filter. And what you do with an ensemble Kalman filter is you start with an initial state, and you have actually samples of the state. Usually it's 64 samples, say, okay? So you have 64 possible sets of images which are describing your reality. That's at your first time point. And then you're going to propagate them through your model. So you literally run this equation. In practice, what that means is running each of those through your convolution neural network to predict what's going to happen at the next time point. And this is what will happen at the next time point. And then you do Bayesian updating, basically, to correct those samples to match the observation. And then you do it again. You propagate, and then you update again. And you keep on going like that. So ensemble Kalman filters are reasonably good for filtering and forecasting with state space models. The reason why it's particularly good for this situation is that you literally use the same code you did to train your CNN. When you do training of CNNs, we use what are called mini batches of data. So maybe you use 64 data points at that time, so 64 sets of images. Literally, all you need to do is put those 64 images as your initial state, pass them through the CNN, and you get your 64 possible outputs. So use the same code. This is what I'm trying to say. I didn't need to recode anything. The ensemble Kalman filter uses the same code you need to use to train the CNN, which I thought was quite interesting. And it's very fast. So doing an eNKF literally takes maybe one step would take a fraction of a second on a good GPU. So what are the advantages? Well, if we know what the convolution neural network is, then we can do filtering and forecasting with very little parameter estimation. We get uncertainty quantification for free because we've got a spread of these samples, and we can make uncertainty quantification on the dynamics as well. And also we can run it on GPUs. So these things can be run very quickly indeed. So you need a lot of data. This is the disadvantage. But I do question whether data is a problem nowadays. There's so much data running around that we could use. And uncertainty quantification on the CNN parameters is possible, but it's hard. And another weakness is that it does not necessarily outperform a standard IDE where you have in a moving window, okay, and when the system is locally linear. Because in that case, the Kalman filter, the standard Kalman filter, is optimal, and we know that maximum likelihood has got certain asymptotic properties, which is asymptotically efficient. So when you've got lots of data, like when we have here, the simple IDE will actually be optimal. But of course, it's much slower. So let's go on to some experiments before we conclude. What I did was the same as Bezenak did. I took North Atlantic Ocean and I divided it into 19 zones. And I actually used the product, this really fully observed product, to train the convolution neural network. And from there, we got the parameters psi. Okay, so in total, we used 76,000 sea surface temperature images. That's the sort of data you need to train a network of this sort. The likelihood function looks like this. This is actually the conditional likelihood function, and to find the maximum likelihood estimates, like you do in a standard statistical problem, use gradient descent, but actually use stochastic gradient descent, because you cannot use all the data at one go. And if you use only mini batches, sort of part of the data, then you can implement a stochastic gradient algorithm to find the maximum. All right, so there are about 200,000 parameters. Takes a couple of hours on the GPUs. I provide all the code online for that. And okay, then you've got this trained CNN, and how do you check that it's doing something reasonable? Well, the first thing I did was just give it a moving target and see whether it can estimate the direction of the moving target. This is the optical flow problem. And sure enough, I've given it something which is moving north. I get arrows which are moving north. This is moving southeast. I get arrows which are moving southeast. So it's not perfect. As you can see, there's a region here where spurious dynamics are being estimated. And here it's assuming that things are going to go round. These things are not perfect, but what's important is that this is a very good model. It's a very good prior model. In the absence of anything else, I would use this anytime. Okay. So it does a remarkable job of capturing the system dynamics, and that's why it's a good prior model. We also get uncertainties on the dynamics. So if we take the ensemble Kalman filter outputs, then all of those correspond to some advection parameters. I can bin those in histograms. So for example, here we are uncertain on what the wind direction is, while in this case, we are very certain what the wind direction is. And then we did some experiments where we left out some of the data. This is a new time period, so we're not using any of the images we used to train the CNN. We left out some of the data and then used the CNN and the statistical additions that I had, so the statistical CNN IDE to forecast what's going to happen into the future. And we compared this with some traditional other methods like spatial Kriging, today's weather is tomorrow's weather sort of idea, space-time Kriging, and a standard full rank IDE. And we used the root mean squared prediction error and the continuous ranked probability score to assess the forecast. And this is what we get on the 19 zones, so the same 19 zones we had before. So there's quite a lot of information here, but basically if something is hovering around 1, it means equivalent performance. If something is above 1, it means that it did worse than the CNN IDE. And if it is less than 1, it did better. So as you can see, standard spatial Kriging and space-time Kriging don't do nearly as well as the standard integral difference equation, which does nearly as well as the CNN IDE for forecasting. Sometimes it does better, sometimes it does worse. There's no clear winner, I would say. But what's interesting is that the CNN IDE required about 100 times less computational effort. I mean, why is this? Because you simply take your ensemble Kalman filter, run it through all the images, no parameter estimation, you're done, right? While with the IDE, you need to estimate the parameters every time, okay? So it took 2 days as opposed to a few minutes with the GPU. Okay. So the speed gain is impressive. So, and finally, just to conclude, we had this idea that, well, if the CNN IDE encodes physics, can we use it to forecast in a totally different applications? And it turns out, yes. So although we trained it on sea surface temperature, we actually, without re-estimating the parameters, we could use it to forecast precipitation, which is a completely different application. So this is basically what we're trying to do. So these are clouds moving north in Sydney. And so the cloud is here, then it's moving a bit north, and it's moving north. And what we did was we wanted to forecast this. So this is out of sample, using just the previous images. And we used variants of the IDE. I'm not going to go into detail, but this is the one which used the convolution neural network. And if we look at the diagnostics, it actually did better than the other models. It even got bang on coverage, and the interval score was also the best. So what's very interesting is that this model was trained on sea surface temperature and yet outperformed other IDEs that were trained on precipitation. So you can encapsulate the physics really well. I think this is the main message of this talk, using the convolution neural network. People did that. And then you can throw it into a hierarchical statistical framework to cater for uncertainty, to do uncertainty quantification and all sorts of nice things. And it actually works very well. Okay, so to summarize, the CNN IDE provides a global prior model for the dynamics. It is versatile, and it has a big role to play in space-time forecasting, where things are governed by partial differential equations. Since dynamical parameters do not need to be estimated, this model is very scalable to large spatio-temporal domains. Here is a list of links. So I've got a preprint, the published manuscript, there's a GitHub page, a bit of a blog post as well, which summarizes basically what I did. So andrewsatm.wordpress.com is my blog page. And the book that Susanna was referring to earlier is this one here. It came out last year. It hasn't got details on the convolution neural network. That is very recent work, but it's got a lot of details on the integral difference equation, which is the starting point for this model. Okay, and that is it. Thanks very much.
Thank you, Andrew. That was excellent. So we do have questions already, and I apologize to Simon because we did miss his question, which was tempted to be asked in the break. So Simon's question was, are there constraints on the kernels, and are wavelets valid kernels here?
No, there's absolutely no constraints on the kernel. So the reason, I'm going back to this equation over here. So the only reason I chose the Gaussian kernel is because it's intimately linked to the advection diffusion equation, right? So I physically know what these parameters are. They're advection and diffusion parameters. As soon as you start to mess around with the kernel, it's valid. You can do whatever you want here. It just, this thing must not explode, and I'm doing some tricks to make sure that doesn't happen. But when you do that, then you do not have the link to the corresponding partial differential equation. So what the parameters mean might not be that clear, but certainly you can put any kernel you want, and wavelet kernels, I've never used them myself, but you know, there are many other kernels you could use which would work, yeah.
Awesome, thank you. There's also a question from Petra. So she's just asking about the initial conditions for the PDE. How important is the initial condition setup and assumptions?
So the initial condition, actually we forget about that pretty quickly because I'm trying to find the slide, sorry. So here's the initial condition. So what it's telling us is that if we have the initial condition at time t, then we know what it is at yt plus 1. When it comes to training the CNN, I assume that the first few images are known. In that sense, I am fixing the initial condition. I'm actually doing a very crude estimate for that using inverse distance weighting. So there is some effect in the first time points for, you know, assuming you know those, but from what I've seen, the effect like disappears straight away. Like at least for this process, within a few time points, it was gone. Yeah.
Awesome, thank you. Another question from Simon. How much did you have to think about the configuration of the convolutional?
Not at all, because I used what the Bezenak did, which they showed they worked. There's a big literature. I'm personally not 100% in touch how these final architectures have been chosen. There definitely is a starting point. Let me go to my architecture, where you use 64 by 64 images because that's what the GPU can handle. I mean, I can't even go to 128 by 128 on my GPU. And then there's this idea of drilling down, until you've got like 256 times 8 is quite small. you know, so we're talking about 1,800. So I realistically can find a linear model, I mean, literally a matrix of size 1,800 times the vector of w's, which might be 80 in my case. If that was not enough, I would have done yet another layer. I think the most important thing is that you don't lose information. So here I've got 64 images of 32 by 32. I apply 1 to 8 kernels, and I get 16 by 16. I don't apply 32 kernels because then I've really condensed my information, and there might be a lot of information loss. So there are these tricks which you start to see when you start reading these papers that people use, and in the end, I just coded it up and it worked. I didn't give it much thought, to be honest.
Excellent. Yeah. Does anyone else have any questions? You are welcome to also click on the participants pane and raise your hand if you wish.
Hi, I'm here, sorry. Were there any more questions, Susanna? Or?
None that I have seen come through yet.
Okay. All right.
But there's plenty of complimentary statements about your excellent presentation, Andrew. So we'll give you a copy of this log afterwards.
Yeah, so I think the slides will be online, and the video as well, if you want to see this. And as I said, I've got all these, especially the GitHub page and the blog post kind of summarize the main message of, I think, of this work.
Awesome. Well, thank you so much. That was really interesting, and we get early marks. So have a great day, everybody. I would just want to also thank, in addition to Andrew, I want to thank Mark Wikle for his excellent technical support again. I also want to thank all of you for participating and attending. It's always good to have these interactions with the speakers. So please enjoy the rest of your day, and we hope to see you at another SSA webinar in the future. Thank you.
Okay, thank you.